All right, example 13 is another classic optimization problem. You take calculus 1 again at some point in your life. You'll probably see a problem similar to this in that class. We have an archtop window, and believe it or not, sometimes it's called a Norman window, named after Mr. Norman. I don't know if Norman was his first or last name. I haven't really researched Norman windows, but I'm calling it an archtop window. It's being built, okay, as we speak. The bottom is a rectangle, and the top is a semicircular semicircle. All right, so here's what it is. You got this rectangular base, and then the top is half of a circle. Got it? And it's one window. If there is to be 12 meters of framing around the perimeter, essentially, then what is the width of the window that lets in the most light? So how do we know this is optimization? We have the most light. We have a constraint. We're limited in the amount of material we can use around the perimeter, or its overall perimeter length, but we're trying to get the most light. So we're trying to maximize sunshine. How do you maximize sunshine? You move closer to the sun? Or you just do all your business not at night? Very good. We're trying to maximize the area. We maximize the area. And we minimize the shades or the mini blinds that we put over it, and we also keep the glass clean so more light comes in. But yeah, we're trying to maximize the area. Maximizing the area for a given perimeter. Now, we need to kind of come over here and label this. If it weren't drawn, then I would probably draw it. There are really two shapes here that you want to consider, a rectangle and a semicircle. Now, you could do this one of two ways. You could label the overall width of the window W, and then that would be fine. You could call this, what, H for height? So those are the basic dimensions needed for a rectangle, right? Length and width, or width and height, whatever you want to call them. What is the important dimension in a circle? The radius, okay? So if you draw a dot here in the middle of the window, this could be the radius. Now, if you've already called the window W, then you would have to call this W halves, right? And I'm already not liking that because now I have a fraction. I have a fraction. There's a presidential joke in there too somewhere. That's what I'm going to do. So in the spirit, like we did up here, of labeling, where did we do that? We labeled this distance y, instead of calling the whole thing h and calling that h minus 5. You want to get in the spirit of labeling the smaller part. So yes, if I call that r, now I can call what I did call w, I can call it what? 2r, and now you're not working with fractions. Or w, right. Either way is perfectly correct. Humbug. Either way is correct. And however you set up the problem, your equations might look slightly differently, but if you proceed with the correct math, you're going to get the same answer. It's just kind of for easiness of use along the way. All right, so now we need to go ahead and write our optimal equation. We're trying to maximize the area. So I'm going to call the area A, and really you can think of it as just the area of the two shapes combined. So what would be the area of my rectangular base now? 2RH, right? It's length times width, but it's 2RH for me. And I'm going to add to that the area of my semicircular semicircle. So what's the area of a circle? Pi r squared, but because it's semi, we take half of it. So pi r squared divided by 2, or you could just call it pi halves r squared. So there it is. There's the area of the window. It's in terms of both h and r, and now we want to get it in terms of either h or r. It doesn't really matter. And in order to do that, we need to get our constraint involved. So 12 meters would end up being the perimeter all the way around. That needs to be 12 meters. So that should be pretty easy to figure out, right? So I'm not going to call it perimeter. I'm just going to call it 12 because that's what we have to work with. And let's see. I'm going to have 2r once. Would you agree? 2r, that's the base. And then I'm going to add to that a vertical piece here on the rectangle, which is H, one on the right and one on the left. So it should be what? 2H. And now the top of the window would be the semi what? Circumference, the semi-circumference. The full circumference is what? 2 pi r. So half of 2 pi r is pi r. Yeah. So 2r along the bottom, 1h plus another h gives you 2h plus the semi-perimeter or the semi-circumference, pi r. Good. Now, we can solve that equation for either h or r. It doesn't really matter. But whatever we do, we're going to plug it into the other one. Which one over here would you rather plug into, H or R? I would rather substitute H, because I don't want to have to plug in two different places, and certainly I don't want to square something after I plugged in. So that's going to kind of guide my reasoning over here. Now notice you do have two R terms, right? But they're not like terms in the sense that the coefficients are not like coefficients. So if that were like a 2R and a 5R, I'd call it a 7R, right? But 2R plus pi r, the only thing I could do is maybe factor out the r and call it the quantity pi plus 2r. I'm not going to do that. I don't want to work with parentheses. So I'm just going to leave them as two separate terms. But I am going to solve it for h. So to solve it for h, I'm going to bring these guys to the other side, and I get 12 minus 2r minus pi r. That make sense? And I'm just going to leave those two r terms as separate terms because they have unlike coefficients. Now to divide through by 2, I just take half of every term, and I get half of 12 is 6, half of negative 2 is 1, and half of pi is pi halves. Would it be negative 12? No, I did kind of a double flipperoonie here. I basically left the 2r on the right, or left the 2h on the right, left the 12 on the left. I got 12 minus 2r minus pi r equals 2h, and then I flip both sides. Yeah, that was a double move. Yeah, I do those sometimes just so that you are forced to kind of wince and say, huh, and then ah. Yeah. So are we all in the same window now, page? Yeah. Are we all in the same window? Yeah, okay. Let's move on. Yeah, I don't have any filters in my brain. There's no filters. Just say what's in there. Let's plug in. A equals 2R times our new H, which is this fantastic three-term dude. 6 minus R minus pi halves R. And then plus pi halves R squared. Yeah, that's what I was saying. We have R terms, but they have unlike coefficients. Minus 1R minus pi halves R. If you want, you could factor out the R and call it negative 1 minus pi halves. And then you can use that as your coefficient, right? But I don't want to have the burden of dragging around parenthesis coefficients. So if they're not like coefficients, I'm just going to keep them as two separate terms. Okay? All right, so then there it is. There's our area formula in terms of the radius. We just need to come up with a reasonable domain for R. R represents the radius of the window. What's the smallest R could be? 0, right? But if R is actually 0, I don't think you call it a window, right? I think you call it a wall, right? Lets in no sunlight. It's like, oh, nice window. Where? Oh, right there. I don't see one. Yeah, the radius is 0. Does it make sense, right? Now, the largest the radius could be of the window would be some positive number, some upper bound, right? I'm not sure what it is. If I just roll out 8 meters of material and say that's the radius of a window, it's not really a window either. So I'm not sure what the upper bound is. So I do know that R has to be some positive number. And I'm pretty sure that when R is 0, there's no light coming in. And when R is at a maximum, maybe my window is just... Could you just say it's 12? I mean, yeah, I would think that it would definitely have to be less than 12. I don't think it's going to be greater than 12 because that's our upper bound for the material. So, yeah, you could do that, 0 and 12. If I do say that it's 12, I don't think 12 is going to be the one that maximizes the sunlight, right? Because if I just roll out 12 meters of material again, I've collapsed it down vertically. There's no window. You just have, some material stapled to the wall, whatever. Okay. Okay, so yeah, I think that's reasonable. So why do I say that? Because I think somewhere between 0 and 12, there's going to be a value that maximizes the area, and that's what I'm looking for, the critical value. So you want to simplify before we take the derivative, or you just want to jump in and use the product rule? Let's simplify. Yeah, I think I'll distribute here, and I get 12r minus 2r squared minus, oh, look, the 2's divide out, and I'm left with pi r squared. Yeah? And then plus the pi halves r squared. So now I have 3 r squared terms. But 2 of them have pi in there. So at this point, maybe, before you take the derivative, you could combine these two. What is negative pi plus pi halves? Negative pi halves r squared. All right, so, all right, here we go. A prime. It happens sooner and sooner every day. It was like 2 seconds off, then it was 3 seconds off. Today it was 6 seconds off. Oh, okay, I was going to say, because I have the atomic clock on my watch right here. This is it. So your watch is broken. Well, I put in an alarm on that. It runs a little fast though, so that's good. Rather than running slow, you're always going to be on time. I'm a couple seconds early. The derivative would be 12 minus 4r minus pi r. And now I set that equal to 0. And at this point now, if I'm trying to solve for r, let's separate the r terms from the number terms. And in this case, I will not do the double flipperoonie, the double move. I'll leave the 12 on the left and move the r terms to the right. But now to get a single r representative, I do want to factor out the r. So at some point it's going to happen. It's easier just to leave them as separate terms all along the way. Otherwise you have parentheses that you're carrying around. And so now I get r equals 12 over the quantity 4 plus pi. Can I simplify that to 12 fourths, which is 3, plus 12 over pi? Can you split up denominators? No, that doesn't work. So don't mess up a good thing there at the end. Now this would be units of meters. So we've already thought about why this is going to be the value that actually maximizes. So we're not going to have to we're not going to justify. I'm not going to say the sentence. That's it. That's the answer. Now, once again, it's kind of a sad story that we're telling here because we're saying that the optimal quantity that maximizes sunlight is going to be when the radius is what type of number? Oh, yeah. I haven't finished answering the question yet. You're right. No, I'm just saying this is the optimal radius. This is what I'm calling the radius. So this is the optimal radius of the window. But it's still a sad story because the optimal radius, or the optimal diameter, if you double it, which is the width of the window, is what type of number? Irrational. So can that window actually be built? No, it can't. So sad. So it's going to be an imperfect window, like an oriental rug. Every window is going to be imperfect that has an arch top. Maybe you can ask for a discount then because it's imperfect. Okay, yes, now, thank you for keeping me on track. Y'all are good at doing that. I am bad at staying on track. We need to answer the question. Okay, what color is the window? Is that what it said? What is the width? Okay, the width of the window. Now, we called the width 2r. So here we go. So we could throw this word in there. So the optimal width is, maybe the word is better here in the sentence. And then you could say 2r, kind of like we did in the quiz, where we said 3 at W. 2r equals, and then just double the numerator, 24 over 4 plus pi meters. Something like that. Now, I think there's one on the worksheet where I ask you for the ratio of the width to the overall height. And that's an interesting question. If you wanted to figure out what the overall height is, let's do that. Because that would be kind of a good number to know if you're the framer trying to frame the opening for the window, right? Overall width and then the overall height, so you can block it in there. So a follow-up question here, the overall height then of this optimal window that really can't exist, what would the overall height be? Is it h? No, because the way I've defined it, h is just the height of the rectangular portion of the window. I need to go up from there another what? R. Good, good, good. So the overall height is h plus r. Now, I haven't found h yet, have I? So if I plug that in over here, that's going to be equal to 6 minus r. Well, r is 12 over 4 plus pi minus pi halves r. So that's minus pi halves times 12 over 4 plus pi. So there is my h. And then plus r is 12 over 4 plus pi. Now, you want to simplify that? I'm just going to put meters. Let's simplify it. Because something interesting happens. This will be good just for kind of working with fractions as well. The 6, yeah.
Oh, can you just get rid of the 12 plus 4 pi right there and then 1 back?
Yes, those cancel. That's good. That's good. Those cancel. So I have a 6 minus, and then over here my 2's divide out with the 12, so I'm just left with what in the top here? 6 pi over 4 plus pi. Now I have two terms. Let's get them together. Let's bring people together. Let's bring things together. We need a common denominator for that, don't we? So I'm going to multiply that one by 4 plus pi over 4 plus pi. You okay with that? And then minus the 6 pi over 4 plus pi. If I distribute now, I can, by the way, put them all over 4 plus pi. Yes, because now they have a common denominator. So if I distribute, I get a 6 times 4, that is a 24. And then I get a plus 6 pi minus 6 pi, holy bovine. What are we left with? 24 over 4 plus pi. That is the overall height in meters. Does it, what? I was going to say, does that number sound familiar? That was also the overall width. So what would be the ratio of the overall height to the overall width? 1 to 1. Yeah, it's 1. So it turns out that the most optimal Norman window that lets in the most sunlight during sunny days would be a window that fits perfectly inside what type of opening? A box. That is a square box opening. Yeah. 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 Not all boxes are square. Some are rectangular prisms, most of them. Anyway. Yeah, that's cool. So, again, nature loves symmetry. Nature loves symmetry. I think I just kind of gave away the answer on the worksheet. But anyway, you can go through the calculations. All right, so this is a good problem because it emphasized, again, labeling small parts and building up from there. If you prefer to work with fractions, that's fine. And then keeping those two R terms that have unlike coefficients, it's a little bit easier to calculate all of the process or all the way through if you leave them as two separate terms. Okay? All right, any questions on the Norman window? All right, the last one. The last one on the notes is similar to the very first question on the worksheet. Because the worksheet is all just kind of random. Force you to kind of think. All right. Find an equation in general form. General form, that's not Taylor form, is it? What if we say it was General Taylor? Can we say it's the same? I guess we need a capital G. Has there ever been a president, General Taylor? Zachary Taylor, right? He didn't last that long. Yeah, he was a general. Yeah. I think it was like the Spanish-American War, or the War of 1812, some war. All right. A general form, remember, is AX plus BY equals C, where A and B and C are what types of numbers? Integers, yeah. So that means no fractions. No fractions. Okay, so that's just thinking ahead down the road. Find an equation for the tangent line to the graph of this function. So that is going to be some cubic polynomial with a negative leading coefficient. So it's going to look something like this. It's going to have, it's going to go out to negative infinity as x goes to infinity. And if you go out to negative infinity, negative times negative is positive. It's going to go up to positive infinity. So it comes in the top, goes out the bottom, and its derivative is going to be a quadratic, so it's going to have maximum 2 horizontal tangents, 2 turning points. So it's going to be something like that. And I want to find the tangent line where that function has a maximum slope. Ooh, that's optimization, maximum slope. We're trying to maximize the slope. Which equation gives us the slope of a function? Its first derivative. So we're trying to find the maximum value of f prime. All right. Now let's look at the graph. Where would this have a maximum slope? Yeah. If it does look like this, it would be at the, what do we call that value? The inflection value. If this is what the graph looks like, here is where the slope is the most positive. Yeah? So it could be at the inflection value, but not every cubic looks like that, right? Just because its derivative is a quadratic means it can have at most 2 horizontal tangents. It could look something like this. It could be a monotonic decreasing function. Where would the slope be a maximum there? Where it's the what? Where it's the least negative. Yeah. Where would it be the least negative? It would still be at the inflection point. Yeah. Okay. So there you go. We're essentially trying to find the inflection value now of f, which means we're going to need which derivative? The second derivative. So be careful. Whenever it says you're trying to find the maximum of something, that function that represents that something is your starting function. You always need to find its critical value. So like the first row on the worksheet, you want to find the maximum rate of change. If you're trying to find the maximum rate of change, you need to take the derivative to get the rate of change function, then take its derivative to find its critical values. Okay? So having said that, let's proceed. I need to find that point. So I need the first derivative, and that's going to be 0 minus 2 minus 2x minus x squared. This is my slope equation. So this is the now starting place for my optimization work. Notice it is already in terms of a single variable. I don't need a constraint to get it in terms of a single variable. So I need to find its critical values. Critical values of any function are when its derivative is equal to 0. So it ends up being the second derivative. Now, if you don't want to do that, you could call that function something new like s of x for the slope equation, and you could just say now that I'm finding s prime of x. That's fine. We've already thought about it, though, and we know we're finding also the inflection values. So its derivative will be negative 2 minus 2x. We said it equals 0. Find the critical values, and we get negative 2 equals 2x, which means x equals negative 1. Now, here's where you want to be careful. That is an inflection value. How do I know that that's going to be where the slope is at a maximum and not at a minimum? Well, think about the derivative function that we just looked at. It's linear, right? There's what?
There's no minimum.
There is no minimum. How do you know?
Because it's decreasing, as it approaches positive and negative.
What's it? What's decreasing?
Negative.
The slopes are always negative. Because you're saying f prime is always negative, right? Yeah, it is. Because if you factor a negative out of there, you get negative 2 plus 2x plus x squared. And you know that this is always positive, right? Always positive. Maybe? I don't know. This 2x could be... It wouldn't? It wouldn't be ever bigger than the x squared? Okay, so you can reason it that way. I like that. You can also see maybe where it has x-intercepts, and you'll see that it doesn't. They're all imaginary. So that's always positive, and then times the negative makes it negative. You could justify it that way. I like that. You could also look at the derivative of the derivative, right? This is the one that gave us the critical values. It's a graph. It has an x-intercept here at negative 1. This negative 2 minus 2x. And what's the slope? Negative 2. So this is what the graph looks like. So notice s prime is less than 0. I'm sorry. S prime is greater than 0 for all x less than negative 1. Everywhere to the left of negative 1, that graph is positive. And S prime is less than 0. This graph is negative for all x greater than negative 1. Yeah? So anytime you have something changing, a derivative changing from positive to negative, at a point, you know it's a local max, right? But this inverted capital A, and it's true, because it's a line, we know it's never going to cross the x-axis again. So not only is the derivative positive just to the left, but it is everywhere to the left. And not only is the derivative negative just to the right, it's negative everywhere to the right. And therefore, it's not just a local max, but an absolute max. Absolutely. Okay, good. So a couple ways to reason it. If you don't have to justify, is it even worth checking to make sure it's a max and not a min? Probably want to think about it a little bit. Now, if it's a multiple choice question, and one of the answers is no maximum exists, then you would definitely want to check, right? But if that's not an answer choice, you know that it has to exist, and if you only have one critical value, guess what? By process of elimination, it's it. Okay, so now we answer the question. We want the equation of the tangent line at x equals negative 1. So now it's like a brand new question, right? What do we need for the equation of a tangent line? Slope and a point. I don't have either, but I have half of the point. So let's go ahead and find the point first. The point is going to be negative 1, comma, and how do I find the y value? Do I plug it into f, f prime, or f double prime? F, good. So it's going to be, I'll just say f of negative 1, just to kind of show my method. And help me out here. I get 2/3 plus 2 minus 1 plus 1/3. When I plug it back into the function. All right, and so remember, did it come out to be 2? Yeah. This is something that my daughter's having a hard time with right now because I don't think it's explained to her. The commutative and associative property of addition allow you to add anything together in any order you want. So, you know, I think they're taught just to go from left to right. It's always safe. Just go from left to right. Always safe, right? Go from left to right. So then, so she's struggling with like getting a common denominator here, so she can add. And you know, y'all know better than that, right? Y'all have supple minds. Y'all are agile. 2/3 plus 1/3 is 3/3 or 1, and then 1 plus 1 is 2, and you're done. So unfortunately, they're teaching box methods. You know, at the lower methods, right? One size fits all, safe for everybody. One algorithm fits all. And they're not. Oh, there it is. And they're not having the discussions about those wonderful properties. Okay, so now we have a point. Now we need the what there? Slope. How do we find the slope at a point? We plug it into. We got 3 machines here: f, f prime, and f double prime. F prime. Okay, cool. So we already have it. So f prime of negative 1, always indicating our method, showing our notation. We get negative 2. Plus 2 minus 1. Is that right? Negative 2 plus 2 minus 1. And if what we said was true, that better be a negative number, right? Oh, good. It's negative 1. So there's the slope. All right, so now we have all our ingredients kind of measured. Put in little bowls. Real easy to make the recipe now, right? We just drop it into our template. Now, even though we need to end up with our equation in general form, we still use Taylor form to construct our equations, and then we will modify accordingly afterwards, okay? So let's drop it in. We get y equals the y value, which is 2, plus the slope, which is really minus 1, times x minus negative 1, the x value, which really becomes x plus 1. Now, if it didn't specify the form of the equation of the line, you're good right there. You walk away. We're going to go ahead and distribute now and expand. So we get 2 minus x minus 1, which is y equals negative x plus 1. Is that where we stop? No, that's not general form. That is another useful form, right? That is the slope-intercept form. All you have to do to get it into general form, and there's no fractions here, which is cool. If you had any fractions at this point, you would want to multiply both sides by the LCM on both sides and clear it out. But we just got to collect our x and y on one side. So positive x plus y equals positive 1. And this is likely, like on a multiple choice, it wouldn't say to put it into general form. It's not necessarily something that you're going to have to know the name of. But this would be like an answer choice, and you would have to know, oh, okay, I need to get it into that form. Now, of course, if you multiply both sides by -1, it changes all the signs, so be aware of that. If you ever have like some positive and some negative terms, you might not have the exact answer. Just multiply both sides by -1. Now, in this case, I don't think this one is preferable here on the bottom because it's so darn what? So darn negative. And we don't like that, right? We prefer to stay positive. But they are equivalent. So again, if you find yourself like maybe collecting your x's and y's on the opposite side of an equation, you may find that all your terms have the wrong signs. Just change every single term. The sign of every term. Don't change every term. Like don't make a 5 a 7. Okay, we be done. We be done. Any questions on optimization? It's not so bad, right? Not so bad, not so bad. Kind of makes sense. Kind of makes sense. They're word problems. Ladybug farming, maybe not so much a real world problem. Okay, so test tomorrow. Test tomorrow. Oh, yes.